Okay, in this tutorial we're looking at section 7.5 on second derivatives. Okay, if we differentiate f of x, we get f dash of x, or dy dx, known as the first derivative. If we differentiate f dash of x, we get f double dash of x, or d squared y on dx squared, known as the second derivative. The second derivative tells us the rate of change of the gradient. Okay, the third derivative is denoted as f triple dash x, or d cubed y on dx cubed. And we can keep going with these, and we say that nth derivative is denoted as f to the n of x, or d to the power n y dx to the power of n. Okay, so basically we're just finding our derivative and then differentiating it. Okay, so I'll have a look at a worked example here. Okay, so this one here we've got f of x equals 4 times the square root of x to the power 5 over 3x squared. Okay, in order to find our second derivative at 9, what we need to do is firstly rearrange this. We can do a little bit of work here before we find our derivatives. Okay, because we can say, well, this is equal to 4x to the power of 5 on 2 over 3x to the power of 2. Okay, when we do that, okay, then we can say, well, f of x is equal to 4 on 3 x to the power of a half. Okay, so we just do a bit of rearranging here. Don't need to look at that and go, oh, I'll go do the quotient rule or anything like that. They're both polynomials, so we can cancel down. So we find our first derivative by saying f dash of x equals, well, our half needs to come down the front and make it 4 on 6 x to the negative a half. And we can simplify that a little and say that we've got 2 on 3 x to the power negative a half. Okay, now we can do our second derivative, okay, which is taking the derivative of this function. So our negative half can come down the front, okay, and we get negative 1 on 3, okay, x to the power of negative 3 on 2. Okay, x to the power of negative 3 on 2. Okay, which means we can write it a bit differently, and we can say it's 1 over 3 times the square root of x, and so it'll be negative x cubed. So it'll be negative 1 over 3 times the square root of x cubed. Okay, and now we just need to find f double dash of 9. Okay, so we simply let x equal 9 in here, and so we've got negative 1 over our 3 times the square root of 9 cubed. Okay, and when we do that, okay, we get negative 1 over 3 times 27, which equals negative 1 over 81. Okay, and we're done. So we'll keep moving on. We'll look at this next worked example. Okay, so we need to find d squared y on dx squared, or our second derivative, for y equals x squared log to the base e of 3x plus 5. Okay, so for this one we are going to need to find our product rule. Use our product rule, sorry, so we can say, well, g of x equals x squared, h of x equals 3x plus 5. That means that g dash of x is equal to 2x, and h dash of x, this should be log to the base e of 3x plus 5, will equal 3 over 3x plus 5. Now it's the derivative of what's inside our bracket here. Okay, goes on top over what's inside our bracket. Okay, that's our quick way of doing the chain rule for these. Okay, so bring it together. Okay, well, we've got to do our, remember you can't stuff up the order with our product rule, so we can go g of x times h dash of x. Okay, will give us 3x squared on 3x plus 5, plus we go the other way, 2x log to the base e of 3x plus 5. Okay. So now that we've got that, okay, we can take our second derivative, okay, we can take the derivative of this to find our second derivative. Okay, so there's a couple of ways we can do this one. So what we'll do is we'll do a double product rule. So we're going to look for f double dash Now what I'm going to do is say f dash of x, just going to change this one a little bit and make it 3x squared times 3x plus 5 to the negative 1 plus 2x log to the base e of 3x plus 5. Okay, so we're going to look at this first term here. Okay. Now I'm still going to use g and h. Okay, it doesn't matter too much. So I'm going to say, well, g of x equals our 3x squared. Okay, and our h of x equals 3x plus 5 to the negative 1. So g dash of x is going to equal 6x, and h dash of x is going to equal, so this has to come down the front. Okay, so we get negative 1 times our derivative of what's in here, which is 3, okay, times our 3x plus 5 to the power negative 2. Okay, so all we've done there is use our shortcut for the chain rule, which is negative 3 outside of 3x plus 5 to the power negative 2. Okay, so now again we can bring it all together, okay, and say this first part at least is going to be, well, we can go this by this, okay, which is going to be negative 9x squared outside of 3x plus 5 to the power of negative 2, okay, plus 6x going the other way, times 3x plus 5 to the negative 1. Okay, so we can make that a little bit nicer and say negative 9x squared over 3x plus 5 squared plus 6x over 3x plus 5. Okay, so getting there. Okay, so what we could do is we could make this a little bit nicer. So I'm going to keep running through simplifying this a little bit more, because what we could do is multiply this side by a 3x plus 5. So we're at negative 9x squared plus 6x outside of 3x plus 5 all over our 3x plus 5 squared. So that means we've got negative, actually I'm probably going to run out of room if I do it over here, or come up here. Means we've got our negative 9x squared, okay, plus 18x squared plus 30x, okay, over our 3x plus 5 squared. Negative 9 plus 18 will give us positive 9x squared, okay, plus 30x over our 3x plus 5 squared. Okay, so I'll leave it there at the moment. Okay, so that's a derivative of this first bit. Now we've got to do derivative of this part. So again, we're going to say, well, g of x is equal to 2x, h of x is equal to our log to the base e of 3x plus 5. Okay, g dash of x, well, that's going to equal 2, h dash of x. Okay, well, it's actually what we had up here. Okay, so we're going to get our 3 over 3x plus 5. Okay, we can bring it together. We'll go this way first. Okay, and say, well, we get 6x over our 3x plus 5. Okay, and we also go this way and say that we get 2 log to the base e of 3x plus 5. Okay, now we can bring our all our parts together. So say f double dash of x. Of course, well, we've got our 9x squared plus 30x over our 3x plus 5 squared, okay, plus 6x over our 3x plus 5 there. Okay, so you see we're actually getting some terms here that are the same. Okay, plus 2 log to the base e of our 3x plus 5. Okay, so getting there. Okay, so what we can do is, again, we can fix up this term and say f double dash of x equals our 9x squared plus 30x. Okay, so we can do like we did down here. Okay, and so we're going to get this part of our equation again, which is going to be plus 18x squared plus 30x. Okay, over our 3x plus 5 squared plus our 2 log to the base e of 3x plus 5. So f double dash of x well, we've got 27x squared plus 60x, okay, over our 3x plus 5 squared plus 2 log to the base e of 3x plus 5. Okay, and we're done. Okay, so we'll keep moving on. Okay, so we can use, we can find our second derivative using implicit differentiation. Okay, so we'll look at wet example 19. So it's saying if a and b are constants and y equals x times the square root of a plus bx squared, show that y times d squared y on dx squared plus dy dx squared equals a plus 6b x squared. Okay. So to start off with, we want to write the equation and square both sides. Okay, so we're going to, this equation here, we're going to square both sides and say that then that we've got y squared equals x squared times a plus bx squared. Okay, and when we expand those brackets, then we're going to get y squared equals ax squared plus b x to the 4, sorry, this shouldn't be squared. Should be squared there, sorry. Put my squared in the wrong spot. Okay, so we get to that. Okay, so what we do is we can say our d dx of y squared equals d dx of our ax squared plus our d dx of our bx to the 4. Okay, so remember from our previous section about this, okay, we take our derivative with respect to y here and say our 2y, but then we're going to times it by dy dx. Okay, we say that equals, well, the derivative of this with respect to x is going to be 2ax. Okay, and the derivative of this with respect to x is going to be 4bx cubed. Okay, so getting there. Okay, so we've got to take our derivative again. Okay, so we do the same process all over again. We say we take d dx of our 2y dy dx equals d dx of our 2ax plus our d dx of our 4bx cubed. Okay. So for our first term, we need to use the product rule. Okay. So when we do that, okay, what we get is we get, when we take the product rule of this, so we'll be taking the derivative of this and that, okay, means that we get 2y, okay, d dx of dy dx, okay, plus dy dx, okay, of d dx of 2y, okay, equaling, well, derivative of this with respect to x is going to be 2a, derivative of this with respect to x is going to be 12bx squared. Okay, so when we get this, well, we're really multiplying them through, so we get our 2y d squared y on dx squared, okay, because these are essentially the same thing, okay, plus our, here, we get our derivative of this with respect to y is going to be our 2, okay, times our dy dx, so we'd have to times this by our dy dx, but we're also timesing it by dy dx, so we can say it's dy dx squared. Right, and of course that equals our 2a plus our 12bx squared. Okay, so we can just rearrange some things there. Okay, to say that we get, well, we divide everything by 2 to get our y d squared y on dx squared, okay, plus our dy on dx squared equals our a plus 6bx squared as required. That's what we're looking for. Okay, so we've had to use our implicit differentiation in a couple of ways. Okay, so we can also use parametric differentiation to find second derivatives. So this is really important. We might think that we can use a chain rule on second derivatives to say that d squared y on dx squared is equal to d squared y on dt squared times d squared t on dx squared, and cancel these two out like we would with our chain rule. But this is incorrect, okay, as dt squared does not equal d squared t. Okay, so it's really important to realise that we can't use that. Okay, but what we can use, okay, is d squared y on dx squared is equal to d dt of dy dx times dt dx. Okay, so we can use that, okay, to solve some different problems. So we've got one more worked example to go in this video. So we've got worked example 20. If x equals 3 cos of t and y equals 4 sin of t, find the second derivative in terms of t. Okay, so what we're going to do is start off by saying, well, we've got x equals our 3 cos of t. Okay, so we get dx dt then is equal to minus 3 sine of t. Okay, and we say, well, y equals 4 sine of t. So dy dt is going to be equal to 4 cos of t. Okay, so we've got that part so far. Okay, so when we keep working through this, those people that have been following my videos will have seen we actually did the first part of this in our last tutorial. Okay, so we'll keep working through. Okay, so we say that dy dx equals dy dt times dt dx. Okay, well, our dy dx, okay, that equals our dy dt, which is our 4 cos of t, times by, well, we've got dx dt, not dt dx, so we're going to make it 1 over minus 3 sine of t. Okay, so dy dx equals minus 4 on 3 cos of t over sine of t, which equals minus 4 on 3 cot of t, because cos on sine is cotangent. Okay, so we've got that first bit. Okay, so we know then our dy dx, okay, is that. Okay, so what we can do is we can take dx, ddx of everything, so we can say d dx of our dy dx equals our d dx, okay, of our minus 4 on 3 cot of t. Okay, so what that means, okay, then is we're actually going to undo this identity that we did and go back to there for this side. This side here, I'm going to bring everything over here. Well, that is our d squared y on dx squared, okay, like we want. Okay, and we're saying then, okay, that is going to be, so we're going to use our cot part equals this, okay, and we're going to use our implicit differentiation, so actually we're going to say d dt of minus 4 cos of t over 3 sine of t dt dx, right, is what we're looking at. Okay, so we're going to use the quotient rule on this because we've got one function divided by another function. Okay, so when we do that, our d squared y on dx squared, okay, they haven't gone through the full quotient rule process here. Okay, but remember, we've got to be the derivative of this times this, take the derivative of this times that over this squared. Okay, so, now that sounds like a mouthful, but we end up with, we bring our negative out the front. Okay, and so we've got negative, okay, outside of, well, we're going to take the derivative of this part, so d dt of our 4 cos of t times by our 3 sine of t, okay, minus our d dt, okay, of our 3 sine of t, okay, times our 4 cos of t, okay, all over, And it's this one squared. It's always 1 on the bottom squared. 3 sine of t squared dt dx. Okay, so when we do this, okay, got our negative out front. So we know cos goes to negative sine. Okay, so we've got 4 times 3 is 12, and we'll get our negative from our derivative to make it negative 12, and we'll have sine and sine, so we can say that's sine squared of t. Okay, and on this one, well, we know our sine goes to cos. Okay, so we're going to take, and again we've got our 4 times our 3 gives us 12, cos squared of t, okay, over our 3 sine squared of t, which we can just say is our 9 sine squared of t, okay, and that's dt dx still. Okay, well, we should hopefully see here that we know sine squared plus cos squared is equal to 1. Okay, and with our multiplication of our negatives through here, we can say then we end up with our 12 on our top line, because our sine and our cos will cancel out, over our 9 sine squared of t, okay, dt dx. Okay, we need to substitute our dt dx as 1 on dx dt. So we now say that we've got 12 over 9 sine squared of t. Well, we know what dx dt is. It's up here. Okay, so we've got to flip it though, because we need dt dx. Times it by our minus 1 over our 3 sine of t. Okay, which means when we do that, we can have our 12 with our 3 cancel out in here, a few different bits and pieces. Okay, so we end up with minus 4 over 9 sine cubed of t. Okay, which, if you like, we can say then that d squared y over dx squared, okay, is equal to negative 4 on 9 cosec cubed of t, since 1 over sine is cosec. Okay. And that's the end. That's all we've got for this video. So, look, second derivatives aren't horrible. Okay, obviously they get harder when we put in our parametric and our implicit differentiation. That's always going to make our questions more difficult. But essentially, you're just taking the derivative of the derivative, and you just need to use whatever skills that we've already built up to be able to do that.